Okay, so here in the final section of the muscle chapter, we're going to be talking about, well, a couple of different things. We're going to start, though, with the other means of changing our force of our graded contraction here, and that was changing stimulus strength. So in the last video, right, we talked about how we can change, we had sort of undergo what we call wave or temporal summation, right, where we had a bunch of different of stimuli coming in kind of one after the other. And the faster they came in and the more of them there were, the more we had, Baxter's coming in to join me apparently, the more we had, hi Baxter, sort of stronger contractions, right? The other way we're going to do that relies first on the idea of something we're going to call a motor unit, right? So this is what a motor unit is here. And the thing with a motor unit is, right, if you think back to a muscle, right, it's a bundle of bundles, right? That's the whole idea. So we've got a whole lot of muscle fibers in any given muscle, maybe a billion, literally a billion could be in a single large muscle. And each one of them is wired to a neuron, but they don't all have to be wired to the same neuron. Okay, and in fact, they're usually wired to a bunch of different ones. And a single neuron, right, might be wired to 2 or 3 or 4 or 5 or 100 different muscle fibers, right? And in doing so, that one neuron then exerts control over a subset of that muscle. This is what a motor unit is, right? So here in kind of our cartoon example, right, we're going back to our frog muscle. Here we've got 3 different motor neurons, a red one, a purple one, and an orange one. The red one is connected here to this muscle fiber, here colored red conveniently, and this one, again, colored red. Purple one has this guy, purple, purple, and purple. The orange one has orange, orange, and orange. Each of these then, this red motor neuron and the 2 muscle fibers that it's attached to are one motor unit. The purple one and its 3 purple muscle fibers are motor unit 2, and the orange one and its 3 orange muscle fibers is motor unit 3. Now, one neuron can go to multiple muscle fibers, but every muscle fiber is only connected to one neuron. So that's an important thing to kind of keep in mind. The way motor units work is a little bit different in invertebrates. So here's kind of a unusual example of a vertebrate motor unit, right? One motor unit neuron and its 3 muscle fibers. Here, the way it works in invertebrates, right? So you have an arthropod in this particular case. We have what are called overlapping motor units, okay? Where we've got 2 that are excitatory and 1 here that's inhibitory. Polyneuronal multi-terminal innervation, okay? It doesn't really matter here, except that basically the way that a motor unit works in a muscle and an arthropod is that we turn on or turn off a motor unit using different neurons. That's really the only big difference there. Now, it's a little more complicated than that, but that's kind of where we're at. So the reason this becomes important for us, right, is that if we want to generate different amounts of force, right, we can use different motor units because it's going to be not the whole muscle necessarily, but it's going to be a part of it, right? And the idea behind that, okay, the idea behind changing signal strength there is what we call recruitment, right? Where we can bring in some motor neurons, some of our motor units, not others. We can bring in 20% of them or 50% of them or 75% of them. And in doing so, we can also exert control over the force that we apply. And when we think about recruitment, okay, we're going to talk about a concept we talked about before, right, which was threshold and 3 different levels of stimuli, right? A threshold that's below threshold, or a stimulus that's below threshold, subthreshold, something that meets and exceeds potentially threshold, and then maximal stimulus from there. And we'll see what this looks like in the cartoon in a second. Basically, the idea here is that the more motor units we bring in, the more powerful the contraction is. But eventually we're going to get to a point where we're going to be maxed out, right? That's what maximal stimulus ultimately really is. So let's just really just look at the cartoon here, and be kind of maybe a little bit easier in terms of explaining what's happening. So this diagram, I like it, but it's complicated. It's got 3 different parts to it, each of which is directly related to the other 2, right? So here we've got 10 different stimuli in terms of the voltage supplied to the muscle, right? Here we've got the number of motor units, again, 10 different examples of that. And then down here we've got myograms. There are 10 here, believe it or not, even though you don't see it at the beginning, for reasons we'll talk about in a second. Again, each of which that corresponds to the one directly above or below it in the column. So let's start here with the voltage part, just to kind of work through here. The idea here is for weak stimuli, ones that don't meet threshold, so these first 2, we don't actually have any contraction at all. There are no motor units that actually get stimulated. And because no motor units get stimulated, no tension is applied and nothing happens, right? But starting at 3 and moving our way upward, the stimulus is strong enough to stimulate at least some of the motor units, right? And so we start to see them get filled in here, right? And as strength of stimulus increases, more and more and more and more and more motor units get recruited, right? And as more and more recruitment happens, the force, right, the tension gets bigger and bigger and bigger and bigger and bigger. Now, eventually, we've called all of our buddies to help us move, right? At some point, your Rolodex is going to be empty and there's no one left to call. You can continue to increase the stimulus, but it's not going to have any effect, right? So once we've called all of our buddies, we're now at maximal stimulus and maximal contraction because there are no more motor units untapped left to bring in. Now, the way that recruitment works relies on the idea that not every muscle fiber is created equal. Some muscle fibers are fat, some muscle fibers are thin. And the fatter the muscle fiber, the more myofibrils are within it. And the more myofibrils that are within it, the stronger it is, right? So the bigger, the fatter a muscle fiber is, the stronger it is. The smaller it is, the weaker it is. And then we're going to call them in order, in reversing order of size. Okay, this is called the size principle. And again, this is just what this looks like, right? We're going to call in the weakest ones first. And that might seem counterintuitive to you at first, but remember, when we're first starting off the contraction, right, this is the idea you're picking up a baby bird, right? You're holding a kitten. You don't want to, grab a hold of the thing and crush the thing, right? You want to start gentle. You want to start as gentle as you possibly can. So we're going to start with the weakest ones. And if the weakest ones aren't sufficient, we're going to call in their big brothers or big sisters, one supposes, right? And add a little bit more tension, right? And only when we really need to call in the big guns are we going to do it, right? Only at maximum tension are we ever going to actually bring these guys in. Okay, so the size principle starts weak and works its way up stronger. Now, there is kind of an interesting thing that happens here. I'm not going to worry about this guy over here right now. This is something that I just don't think I can explain over a video. But this over here is pretty interesting to me anyway. And this is the size or the length tension relationship. Okay. And the idea here is that for a skeletal muscle, there is an optimal length, right, at which we can generate the most force. And as we go longer or shorter from that length, we get weaker and weaker and weaker, right? If you've ever been in the gym and you've wondered why you feel really strong during some part of the exercise, but as you complete it, you get weaker and weaker and weaker. It's harder to actually get that weight all the way up, right? If you're doing a curl, for example, right, it might be very easy to get the weight to, I can see this, get the weight to here, right? But every movement above this, you feel weaker and weaker and weaker. This is why, okay? So your optimal length for force is somewhere between 100 and 120% of maximum length. So a little bit stretched is actually where you're strongest. And as you stretch beyond that, you get weaker. And as you shorten, particularly as you go below about 80%, you get weaker in a hurry. Okay. And the reason for that goes back to something we talked about way back when, right, in the first couple of videos, with the cross bridges. The strength of contraction, the force that you can apply, is directly proportional to the number of cross bridges you can form, right? It's like being on a rowboat, right? The more people you've got on the oars, the stronger you can be, the faster you can go, right? And as you stretch, right, as you stretch the muscle, you pull the Z discs apart and you move a lot of these myosin heads out of contact with the thin filaments, right? And you're only left with part of them, right? So these guys are trying, but they can't do anything, right? There's nothing for them to pull on. So they're weaker, right? So like if you're on a big boat and you tell half the oarsmen or oarswomen to stop rowing, right? And the same thing happens when you get shorter. You end up with a situation where a lot of these myosin heads actually get kind of crumpled together at the ends as the Z discs close in, and they're no longer useful, right? They can't be brought to bear either. And so again, you lose tension as you move through the length of that muscle stretch and contraction. Now, final bit here in terms of the physiology here that's kind of useful for us is that we need to remember there are multiple different ways for ATP to be produced within a muscle fiber, right? We have a couple of anaerobic ways, and we have a aerobic way. The first anaerobic way, the one that we do the first, right, is our phosphatase pathways, right? Things like creatine phosphate. A very, very quick, easy way for us to make ATP, right, so that we can relax, right? And we can't continue to contract unless we relax. It's a whole big thing. The other pathways that we've talked about, right, and these are really the more important ones in terms of generating a lot of ATP, are glycolysis and oxidative phosphorylation, right, respiration. And as it turns out, certain muscle fibers are going to prefer one or the other. And the more of those muscle fibers are present in a muscle, the muscle is going to prefer one pathway or the other also. Okay. And the reason that becomes important for us, right, if we think back to how all this stuff works, right, is that we generate different amounts of ATP at different rates and with different requirements. Okay. So if we're going to be focused on glycolysis, we can generate ATP really fast, right? And generate, you know, not nothing, right? You can generate kind of a moderate amount of ATP, okay? And our limiting factor here is glucose. We don't care about oxygen at all, okay? On the other hand, if we're going to be aerobic, right? If we're going to be respiratory, it takes a long time, right? It's a slower process. We can make a lot of ATP, okay? But we have to have both glucose and oxygen, okay? So again, there are trade-offs to picking one over the other. And as it turns out, right, it actually becomes fairly easy to see which different muscle fibers prefer which different pathway because of their requirements, right? So here we've got, and again, these are shades of yellow and orange here, but the more you rely on respiration, the more oxygen you need. And so we're going to have in those muscle fibers a lot of myoglobin, right? And just like hemoglobin, when myoglobin binds to oxygen, it turns bright red. And so a fiber that relies on respiration is going to be a much darker, redder color. Same thing here with fibers that rely on glycolysis as their primary means, right? They're not going to have any myoglobin because they don't care. They don't want oxygen, okay? And so they're going to be paler, right? This is the old light meat, dark meat kind of thing that happens when you go to Popeyes and you order your 5-piece, right? you get, don't go to Chick-fil-A, go to Popeyes. You get a little bit of light meat, right? Stuff that's there for fast, high intensity action, breast meat, for example. And you get stuff that's there for not high intensity, but slower, more low intensity activity, right? That's the dark meat. That's what that comes down to. And so we can classify muscle fibers, and kind of extrapolating from their muscles themselves, as being oxidative or glycolytic. And just like the process itself, the activity of the muscle and the muscle fiber, fast twitch or slow twitch, is built around really one of these two different means, fast glycolytic or slow oxidative. We'll worry about these fast oxidative glycolytic in the middle here just in a second. So your slow oxidative, right, your red meat, your dark meat, right, relies on respiration, right? So it's highly resistant to fatigue because it can make a lot of ATP, right? It has a lot of myoglobin and a darker color, but it's not for high intensity, right? It's not for doing parkour or whatever you kids are doing these days, right? And so they're going to be typically smaller fibers, right? They're going to be the weaker ones because they don't require as much potential force to do what they're doing. And they are, of course, slow twitch. Glycolytic, fast glycolytic, on the other hand, right, are fast twitch. They are the gastrocnemius of our example from before, right? And so they are easily fatigued, right, and have very little myoglobin, right, to none, really, right? And they tend to be paler as a result, and because they are for high intensity, high force kinds of activities, they're going to be the big fibers, right? They're going to be the ones that get recruited last. Related ideas here, right? Blood supply, right? If you're going to require oxygen, you require a lot of blood supply. So it's going to be a lot of capillaries in the area. But if you're glycolytic, you don't need it, right? There'll still be capillaries, but you don't need as many, okay? And again, we think about posture, right, versus activity. Oxidative for long held contractions, fast glycolytic for short bursts of activity. All right, simple as that. Now these middle guys here, these fast oxidative glycolytic ones, through exercise. So you're born with slow oxidative and fast glycolytic fibers. Through training, you can turn fast glycolytic fibers into fast oxidative fibers, right? They can be fast twitch, but they can rely as heavily, if not more heavily, on respiration than glycolysis. And these are really the best of both worlds, because they're for high intensity activity, right? But they have pretty good resistance to fatigue, right? You're not going to wear them out quite as quickly. So they're of great value to us. Okay, let's look at some examples here of what's happening, or one example here of how some non-vertebrates use their muscles in the most efficient possible way. So if you ever wondered how possibly a bug can sustain the wing beat frequency that's required for it to fly, it's actually a pretty ingenious mechanism. There's two different ways that they can do it, and both rely on the fact that they have an exoskeleton rather than an internal skeleton. So that exoskeleton, that cuticle, is rigid, but it's also a little bendy, right? And so when they pull on that exoskeleton, sometimes they can store energy within it, right? They can hold energy onto it. So what we're going to see here then are a couple of different ways in which that might happen a little bit. So in cases like a dragonfly here, we have what are called synchronous flight muscles, okay? And by synchronous, what we mean is that they are oriented in the same general direction, okay? They're both attached to the bottom of the cuticle, the bottom of the exoskeleton, and to different parts of the wing. And so we have an elevator muscle that's involved in lifting the wing, and a depressor muscle that's involved in pulling it down. And so to lift the wing, the elevator muscle contracts, That depressor muscle relaxes and the wing flips up, vice versa to bring it back down. Simple as that, right? We can, as we contract though, we can rely on some elastic rebound at the cuticle to kind of pull in the opposite direction, right? To get us to kind of flip the other way. But really where we spend the most time and are the most efficient is with what we call asynchronous flight muscles, which really, really heavily rely on that contraction rebound kind of activity. And in this particular case, the asynchronous, because I say asynchronous refers to the fact that these muscles are not oriented in the same direction. We have vertical muscles and longitudinal muscles, right? Longitudinal that run front to back, vertical that run top to bottom. And neither of them is actually attached to the wing. They are only attached to the exoskeleton, and the wing is attached here to little hinges on that skeleton. So as the vertical muscle pulls down, right, it compresses the thorax top to bottom, and that hinge pushes up. And as that hinge pushes up, the wing goes up. Then those muscles can relax, right? And the elastic rebound of the cuticle, of the exoskeleton, causes the thorax to go up and down, right, to kind of expand in that vertical direction. At the same time that the longitudinal muscles are pulling it shorter, right? As they shorten it, right, it also forces the top and the bottom apart. So we've got some muscle activity and some stored energy causing this vertical expansion, which causes the hinge to go down and the wing to go down. And then we do the opposite all over again, right? We relax the longitudinal muscles, the cuticle lengthens, gets shorter. At the same time, the vertical muscles are continuing to pull it down, okay, and the wing goes back up. And so we don't rely entirely here on muscular activity for this particular activity. We have a little bit of stored energy, a little bit of muscle activity, very, very, very efficient. Okay, all right, so we'll call it good there. On the next video series, we will talk about how we actually control some of this stuff in terms of neurological connections beyond the motor unit.